Hello, everyone. In this lesson, we're going to be looking at Rolle's theorem and the mean value theorem. So we can see Rolle's theorem right here. Go through it. We have a function. It satisfies the following conditions. On a particular interval, it is continuous, and it is also differentiable on that interval. Not necessarily at the boundaries, but it is continuous over those boundaries. And f at a equals f at b. So in other words, the boundaries are at the same level. They have the same y value. If these criteria are met, then there is some value, at least one, maybe multiple, in that interval such that the derivative has to be zero. So let's look at some examples of what that might look like. We might have a really basic function. Let's say we have, for example, y equals f of x is just a horizontal line where we have some value a and some value b. That's obviously a continuous function on that interval. It's differentiable all the way along. Its derivative is just zero all the way along. But the y value at both a and b is the same. There, therefore, is very trivially and obviously at least one value c such that the derivative is zero. In fact, they all are. I can draw, let's say, a function where I have a and b. They have the same value of y, and maybe my function starts out going this way. If it's continuous and differentiable, and it has to get back down to that same level where it started, then somewhere it has to reach a maximum. So somewhere it has to have a slope of zero, and that would be the c value. Likewise, if my function starts out from a, and it starts out decreasing, but it has to get back to b by the time it gets to b, then somewhere it has to have reached a minimum. It has to have turned around. And when it reaches that minimum, it has a slope of zero, and that would tell me where c is. Now, I can see from these diagrams why there has to be at least one such point. The fact is there can be multiple, so I can have an a value and a b value, and they're at the same level, and the function might increase, decrease multiple times in that interval. But it has to have at least one. Otherwise, it can't get back to the same y value. So that's sort of an informal justification for that. Let's look at a formal sort of proof of that. So we have case one. Case one is where we have f at x is just some constant k, where k is any real constant. Well, if that's the case, then f prime at x is just zero. So c is any number in that interval. So any number in the interval a to b. So that's the trivial case. Case two, less trivial. Case two is that f at x is greater than f at a for some x in that interval. In other words, at some point, f of x has gone above that value for some x in that interval. Now remember, that means that it's also higher than f at b because f at a and f at b have the same value. So there must be some maximum f of x. So there must be some maximum in this interval. So if we can find any value of x in that interval that has a higher associated function value than a and b, so there must be some value of some maximum f of x in the interval a to b. And the reason we know there has to be a maximum is it has to come back down, and it's continuous and differentiable the whole way along. So at no point can it start shooting off to infinity. Somewhere there has to be a boundary. There must be some maximum, and that is where f prime of c, for example, would equal zero. So that's in the situation where we can find even a single point. If we know it satisfies those criteria, and we can find any single point that is above the values of f at a and f at b, then we know there must be, whether that initial point was the maximum or not, there must be a maximum. And case three is the parallel of that. If we have some f of x that is less than f at a, for some any could be any one, as long as we can find a single value in that interval that has f at x smaller than f at a, and likewise f at b, then we can conclude that there must be some minimum. Again, because it's continuous and differentiable throughout. So because it's continuous, it can't have any breaks, it can't have any asymptotes, and it can't go off limit, like the asymptote thing. It can't go off to infinity. So there has to be a minimum, or off to negative infinity in this case. So there has to be a minimum in that interval, and at that minimum, f prime at c would have to be 0. So this seems like kind of a trivial result, and it basically is, but it's the starting point, sort of the special case of the mean value theorem, which is pretty important. So the mean value theorem is when we have a function that satisfies those first two conditions. So it is continuous on an interval and differentiable everywhere within that interval, although not necessarily at the boundaries. But we don't know that f at b equals f at a. So Rolle's theorem is a special case of this situation where we do have that additional criteria. The mean value theorem says then there must be some value of c inside that interval such that the derivative of c, so the slope at that specific point c, is equal to the average slope of that interval. So what's given here, f at b minus f of a, is the overall change in the y value, essentially, and b minus a is the overall change in the x value. So this is the average slope over the whole interval a to b. So what the mean value theorem says is that if I have an average, or if I have an average slope for this whole interval, and the function is continuous and differentiable, then somewhere the actual slope of the function must be exactly equal to that average. This makes intuitive sense if I think about this as representing, so think of an example where it's representing speed. Now let's say I drive from Calgary to Edmonton, and I can figure out my average speed over that time by simply taking the distance covered divided by the amount of time it has taken me to cover that distance. That would give me an average speed for that trip. What the mean value theorem says is that because the function that describes my speed, now I don't know what that function is, it's not a simple function, but it definitely is continuous. My speed exists everywhere along that trip. There's no weird gaps where suddenly I have no speed. So even if I'm not going anywhere, my speed is 0. That exists. 0 exists. And it is differentiable. Like the rate of change in my speed exists everywhere. There's no weird gaps or asymptotes. My speed at no point is tending towards infinity, assuming that we're following the laws of physics on the highway. So what the mean value theorem says is that because my speed meets those criteria, if I know my average speed, then I know at least once on the trip I was going exactly that average speed. Now it's possible, unlikely, but possible, that I was going exactly that average speed the whole time. What's more likely is that sometimes I was going a little under the speed, sometimes I was going a little over the speed, but because sometimes I was below and sometimes I was above, I would have had to pass through the actual speed on the way. So essentially, this is saying, I know that that exists. I know that somewhere in there, there's the exact speed. So in order to prove this, we're going to first define. So first we define some function, h of x, as the vertical distance. So vertical distance between the curve y equals f of x, so the one that's just been defined, and the line AB, the straight line that connects. So the straight line connecting the point A, f at A, and B, f at B. So essentially, I'm calling the one endpoint of this interval A and the other endpoint of this interval B, and I'm drawing a straight line between them. So as an example of what this might look like, if this is my function y equals f of x, and I have A and B, whatever they are, then the line AB is just the straight line connecting those 2 points. And h of x is defined as the vertical distance between those 2 things, wherever that might be. Where they intersect, h of x is 0. So let's actually figure out how we can describe that function. So I've got the line AB. I'm going to come up with its equation. So AB, well, I've got a slope is going to be what was defined above. So f at b minus f at a over b minus a. And using point slope form and let's say point A, I've got y minus f at a equals f at b minus f of a over b minus a, the slope, times x minus a. So this is the point slope form using point A and the slope I've just found. So what that means, h of x is therefore equal to the y value of h of x. H of x is a vertical distance, so it's the y value of f of x, which is just f of x, minus the y value of line AB, which is f at b minus f at a over b minus a times x minus a, minus f at a. Okay, so this is the difference. Now, technically, it's the absolute value of those things, but I'm not going to worry myself too terribly much about the absolute value sign. So we've defined a function that basically tells us the vertical distance. So now we're going to prove the mean value theorem. So to prove this, we're going to consider h of x. We're going to consider that h of x is continuous on the interval a to b. So it's continuous because it is the difference between f of x and a linear polynomial, and they both exist everywhere. So is continuous on AB because it is just the difference, in other words, the subtraction, and subtraction doesn't create any discontinuities. It is the difference between continuous function f of x, y equals f of x, and a linear function, which is also continuous. So a continuous linear function. So in other words, h of x satisfies the first criteria. Let's look at the second function. Well, same thing here, really. So h prime of x is simply going to be the difference between the derivatives, because the difference of a subtraction is the subtraction of the 2 derivatives. So h prime of x is the derivative of f of x minus the derivative of that line. Well, the derivative of the line is just the slope, f at b minus f at a over b minus a, which exists. It exists everywhere in that interval because I know that f at x exists everywhere in that interval, and f prime of x exists everywhere in that interval. So this specifically f of x is differentiable. This wouldn't be true if I didn't know that f of x was differentiable, but we've already said that f of x meets that criteria. And looking back to Rolle's theorem, if I consider 3, h of a equals 0. H of a equals 0 because look at the drawing that I made. The line connects A to B. So at A, the vertical distance between the line and the function is 0. And at B, the same thing is true. So h of b equals 0. Therefore, this satisfies Rolle's criteria. So h of x specifically satisfies Rolle's criteria. And because of that, that means that there is some value, so some c in that interval has h prime of x equals 0. So somewhere in there, the derivative of h prime of x is 0. Well, okay, what that means, since we know that h prime of x is f prime of x minus f at b minus f at a over b minus a, there's some value, c, for which that is 0. So then f prime of c minus f at b minus f at a over b minus a has to equal 0, which means that f at b minus f at a over b minus a has to equal f prime at c, which is what the mean value theorem tells me is happening, that somewhere the derivative is exactly equal to that average slope. So that's the proof of the mean value theorem. It's the formal proof. Now, again, informally, we kind of understand why it has to be true, but this is mathematically why it is true. Looking then at why or how we can use this, so we can use the mean value theorem to show, for example, this is a sample question that was asked on a test, an IB exam. So use the mean value theorem to show that if f prime of x equals g prime of x for all values of x in a given interval, then f minus g equals c, a constant on AB. So there's some constant there. So let's define these. So somewhere in there, there's a constant. Okay, so let's say we have, for proof, we're going to let capital F at x equal f at x minus g of x. So then what we have is that the derivative of f, that capital F, has to equal the derivative of small f minus the derivative of g of x, which has to be 0, because we're saying that the derivative of f of x and the derivative of g at x are always equal in this interval. So that has to be 0. So let's consider that capital F prime of x equals 0 for all x in that interval. Well, this means that that must be differentiable on that whole interval. Because I know that the derivative is 0, so the derivative exists. So it must be differentiable on smaller intervals within that. So it must be differentiable on some other interval. I can spell. So it must be differentiable on, say, x1, x2, where x1 and x2 are in the original interval a to b. So by the mean value theorem, looking at the interval x1 to x2, so we're narrowing in on a smaller part of that interval, we have some number c. So there is some c such that, well, I know that c is in that interval. So in other words, x1 is less than c is less than x2. And the derivative of this function has to equal the value of that function at the upper boundary of the interval minus the value of that function at the lower boundary of that interval minus the length of the interval, basically. But I know that f prime of c has to be 0. So that means that f at x2 minus f at x1 has to equal 0. Or in other words, f at x2 equals f at x1. This would be true no matter which two numbers I picked for x1 and x2. So this is true for all, or for any two numbers. So for any pair of two numbers I can choose in that interval. So for any two values in A, B. So what that means is that that function must be some constant. I should technically be using a different letter than not C, but is a constant. So I should have up here not used a C. I should have used, I'm going to go back and change this actually, just so it's not quite as confusing. Different constant, there's some K such that it's a constant, and that the value of the derivative at that K value, it should not be at X. Okay, that I think is a little clearer. So that's what we were trying to prove. So let's go kind of quickly back through this just to sort of see what we were after. So we were trying to show that if two functions have the same derivative in a given interval, then the difference between those functions must be a constant. And that constant has to be in the interval. So we defined the difference between those two functions as a new function. So we called that difference capital F at X. So then, knowing how we derive differences, the derivative of that new function must be the difference between the two original derivatives. But I know from the premise of this problem that the difference between the two original derivatives must be 0 because they are the same. So since the derivative is 0, it exists. It has to exist everywhere. It's differentiable on the entire interval. So let's pick a smaller interval. Arbitrarily, any two values within that interval, it's still differentiable on that interval. And it is continuous because it was continuous in the whole interval. So by the mean value theorem in this new smaller interval x1 to x2, because the function is continuous there and it's differentiable there, there must be some constant such that the derivative is equal to the average slope. But I know that the derivative is overall 0. So that means that the difference between the two endpoints must be 0. In other words, the average slope between some two endpoints, that it's possible for me to pick two values inside the original interval AB such that it's a horizontal line. But essentially, that would have been true for any two values I pick. So no matter which two numbers I pick in the interval A to B, the line that joins them is horizontal, which means that the whole thing must be horizontal. In other words, a constant. And that's what we were trying to show. We were trying to show that the difference between the original function and the second function is some constant. So basically, if I know that two functions have the same derivative, so thinking about this in terms of antiderivatives, when I was finding antiderivatives, the difference between them was the plus c. So this is basically saying that from the other side, and it's now actually formally proving it. That's the thing that we sort of took for granted at the time. That if I consider that the only way to have two functions have the same derivative is if they are vertical translations of each other. This is a more formal way of saying that exact thing, that the difference between those two functions must be a constant. So that's one example of how we can use the mean value theorem. And I'm going to close this video with further evidence that I and my family are crazy math nerds. I was talking to my brother one time, and we were just talking about a number of things, and I was talking about feeling overwhelmed by circumstances, quarantine being what it is. And then I kind of stopped and I said, you can be overwhelmed, and people talk sometimes about being underwhelmed, but is it possible to ever be perfectly whelmed? And my brother paused for a moment and he said, well, yes, by the mean value theorem, it must be possible to be perfectly whelmed. And I said, well, that's only true if we assume that whelming is a continuous function.